we're going to continue impulse momentum, change in momentum, and more. So this is part 1, and I just want to recap a few things that you should know. So for example, momentum. Two big ideas here. One is it's a vector, so it requires direction. Okay, the second is that we have a formula for it. P is the symbol, and for a single object, it's its mass times its velocity. Okay, and it's this second part, both these parts together, that help, once again, in describing the motion of an object. Okay, so it's just one more way. Okay, and so if we're interpreting that equation, the faster or more massive something is, the higher the momentum. Okay? Another thing that you should think of when you're looking at this and we're asking you questions is that a large object moving slowly can have less momentum than a tiny object with high velocity. Okay. All right. So let's see. Okay. Now the last week or so, we've been looking at a change in momentum, and we do know that that's equal to the impulse. Okay. All right. So a change in momentum, what this tells us is that it takes a force applied over some time interval. We're going to get into a lot more as we go through what effect that has. Okay, but these are just the things that you should know. It relates to Newton's second law. Okay, and I went through this proof a little over a week ago, but I just want to make sure that you have it like in your head, that it really is force is equal to mass times acceleration. That's how we learn Newton's law. And now we're going to talk about it as a mass times a change in velocity over time. And it's this part right here, okay, that is equivalent to acceleration. And of course, if we multiply both sides by t, we do end up with the impulse momentum equation. And that we can use a number of ways, so I'm just showing you a couple variations of that, depending on what information you have. And so all of these things are equivalent. Okay, I think that's what I wanted you to know. Okay, so the question often comes up, well, where do we use this in the real world? And I'm just telling you, anyone that's in insurance, as far as investigating claims, or anyone that is in law enforcement or emergency response, truck drivers, anyone that gets into logistics in a company that's transporting goods and services, and there are lots of jobs in that area, they become familiar with this idea. So what they become familiar with is something that we call stopping distance. Or stopping time. And so what I want you to imagine are two different scenarios. And as you well know, I don't draw all that well, but I'll try to make it somewhat similar. Okay, so on the left-hand side, I have a truck that has a load of bricks. So this is a truck plus bricks. So on the left-hand side, I have that. And I want to compare it to an empty truck. There's my empty truck. Okay, looks similar enough. All right, and just for simplicity's sake today, I want to tell you that the truck with the bricks is 2 times the mass of the empty truck. Okay, so it's 2 times the mass. And I also want to tell you that these guys are both traveling at 48 kilometers per hour forward. Now, I'm sure that if you've been carrying like a bunch of people in your car that you haven't before, or your vehicle is loaded down with a bunch of stuff, that you have some intuitive relationship to this. Okay, so if we have twice the mass and they're both traveling at the same velocity, then we know that the truck on the left is going to have 2 times the momentum. Okay, if we just apply it mathematically. Okay, now we're going to let them apply the same braking force. So now we have some force. It's in reverse. So this is the force of the brakes. Okay, and what we notice is that it takes 2 times the stopping time and it takes 2 times the distance for the one with bricks to stop. So I just want you thinking of this as we're working through the next problem. Okay, and I think I also tell you that we never let you forget any of the one-dimensional kinematics equations from the past. So this is a great opportunity for us to take a peek at that. So if we look, we have a 2,250 kilogram car traveling to the west. Okay, so if I were drawing a picture of that, my car, you know me, kind of like VW bugs. And this is, of course, not a very good representation. But it's traveling west, and it's slowing down from 20 meters per second to 5 meters per second. Okay? So in my halves, I've got my mass of my car, and that is 2,250 kilograms. All right. I also have my initial velocity. I happen to be going west, so it's going to be a negative 20 meters per second. West. Okay, that's my initial, and it's slowing down, so my final velocity is going to be a negative 5 meters per second west. Okay, and let's see. How long does it take the car, once again, you see my bad typing, the car to decelerate if the force on the car is 8,450 newtons to the east? So I am going to be applying a force, and that force is going to be positive 8,450 newtons east. So it's positive. Okay, so what I want, at least initially, is I want the time. Okay, and this is a perfect place to use impulse momentum. So what I need is that force times time is equal to the mass of the car, velocity final minus velocity initial. Okay, and if I want to rearrange that for t, I'm going to get delta t is equal to m vf minus vi, and all of that over my force. Okay, but I'm not done. So I'm going to go back up and read the problem again. How far does the car travel during this deceleration? So that we got the stopping time. That's the first variable we're looking for. And then we want to go back to this delta x idea. Okay, and from first unit, we had that delta x over delta t was equal to VF plus VI over 2, right? It was the average. And so, once I figure out what t is, if I want to rearrange and solve for x, this is going to be VF plus VI over 2 times delta t. Okay, so I'm going to let you kind of plug and chug on that, and I'm going to just tell you that your t should be 3.99 seconds, and that your delta x should be 49.9 meters, and it's negative when you calculate it, west. Okay, so I just want to introduce that. I'm going to keep going. All right, so what I want you to do, I want you to do all of your homework in this unit on separate sheets of paper because I may want to collect them from time to time. So on a separate sheet of paper, you're going to complete the following. You would do me a great service if you were to call these stopping distance problems. Okay, so I want you to do those, and then I want to talk to you about the big idea. Okay, so the big idea. I want you to think about this. We've got a trampoline. Okay, we've got a person jumping on the trampoline. Okay, so we know at some point in time that the person is going to reach some maximum height, and then they're going to accelerate downward. Okay, straight up, straight down. And so I want to know, I'm going to think about this, what would happen if instead of being on the trampoline, we had a person that was the same height, falling the same distance, and instead of having the trampoline underneath, they had the ground. Okay, this is what really we can wrap our head around the impulse momentum theorem about. Because if you think about it, they're starting up here at some maximum height where their initial velocity is 0, and at the same point in space, they're going to have the same velocity. Okay? So their change in velocity is the same. There is no change in mass. They're exactly the same. On the left-hand side, if you're jumping on the trampoline, we have no harm. Okay? On the ground, however, we probably have harm. You know, sprained ankles, shin splints, maybe even a broken leg, okay, or worse. And so the question is, why does this happen? Why does this happen? Why? Okay, well, here's why. What happens is we have an extended time interval on the trampoline. The person lands and the trampoline gives way, and the person travels with the trampoline downward. And so we have this extended time interval, which means that they're feeling a smaller force. Okay? On the other hand, we have a very small time interval that the person is interacting with the ground, really small. And so by comparison, in order to have the same change in momentum, the person experiences a much larger force. So this is the big idea. Okay, well, you're not quite done for the day. Okay, once again, on a separate sheet of paper, okay, you can call these impulse momentum questions to answer. So this is your second assignment for today, and this is all I'm giving you today. Okay, now before, let's see, today is Monday, so before Wednesday's class, you need to complete this. And I'm not picking up this packet, so I want you to do your research right on here so on Wednesday we can talk about this. And that's all I've got for you today.